let's talk about how we could apply the first law of thermodynamics for a closed system. And so, as you may remember from Mass and Energy Balances 1, when we talk about a closed system, that means that there's not going to be any sort of mass that crosses the system boundaries. And so if we talked about the accumulation of mass within a system, within a closed system, we know that accumulation of mass is going to be equal to some final amount of mass in the system minus some initial amount of mass, and that will also be equal to our input minus output plus generation and consumption. And so for a closed system, not only do we, for mass specifically, do we not have any generation or consumption, so that's going to be equal to 0, we're also not going to have any sort of inputs or outputs as well, because this is a closed system. And so this right-hand side of the equation is going to be equal to 0. And so that means that the final amount of mass in the system is going to be equal to that initial amount of mass. And so that's what we mean by a closed system. And so for a closed system, there's no input or outputs of mass, but you can still have inputs and outputs of energy, specifically. And so let's consider the following sort of system. And this system is going to be made up of what we call a piston cylinder setup. Piston cylinder system. And in a piston cylinder setup, which you're going to see quite a lot in this course, what we have is some sort of container that at the top is closed off by what we call a piston. And this piston is sealing off some sort of quantity inside the cylinder. You know, this system, it could be made up of a gas, it could be made up of a liquid, even a solid, I guess. But in any case, the system that we're going to be talking about is going to be enclosed entirely underneath the piston within the entire cylinder setup. Right? And so, within this piston cylinder setup, the system, piston can move, and so by moving the piston down, we would be applying some sort of work to the system. We could also heat or cool the system as well by either adding in or removing heat. And so for the system, we could be adding in work, we could be transferring work into the system, and we could also be transferring in heat. Alright, we know from the first law of thermodynamics that energy needs to be conserved in the universe, but within the specific system itself, the amount of energy in that system can change. And so mathematically, for a closed system, we can articulate, or we could describe or apply the first law of thermodynamics like this. For a closed system where the change in energy in the system is going to be equal to the amount of heat that's being added into the system, and also the amount of work that's either being added or released from the system as well. Now you'll notice I wrote a bunch of D's everywhere. These D's are standing for derivative, right? And so what we're talking about here are infinitesimal amounts of energy, heat, or work. It might be a little abstract to think that way at first, because it's slightly different from what you saw in Mass and Energy Balances 2. But really, the way to think of this, or the very simple way to think of this, is that anytime you see these D's, that's like saying that you have a delta. And so instead of the derivative of energy, you could think of it as delta E, but a delta E in which your delta is very, very small. It's infinitesimally small. It's basically 0. And so from that, whenever I write out the derivatives here, that means I'm talking about very, very, very small changes in that quantity. So very small changes in energy are going to be equal to the sum of very small changes in the heat and very small changes in the work that are added into the system. Now, when we apply the first law of thermodynamics to a closed system, it's actually can be presented in two different ways, or it's typically presented in two different ways. The first way it can be presented is in a rate form. And so here, the way we present it is we take our dEs, dQs, and dWs, and we divide them by dt. And so mathematically what we're doing now is we're now taking the derivative of energy with respect to time. Okay? And we also do the same thing with the heat and with the work. By convention, we write this dq dt and this dw dt as q dot and also w dot, right? And so these are the heat rate and the work rate, respectively. All right, and so that's one way to write the energy balance, and the dimensions or the units of this rate form are going to be energy per time, right? And so that's essentially what we define as power. Okay, so with the rate form, your units are going to be energy per time. The other way we could apply the first law, or the other form of the first law that we could use for a closed system, is known as the difference form. And so here, rather than having a differential equation, what we're going to be doing is we're going to be considering the change in the energy between two specific time points, between some time 1 and time 2. So, all right? And so here, for the difference form, what we do is we're going to take our differential in energy and we're going to integrate it between or from the energy at that initial time point and the energy at that later time point, t2. And so as a result, what we end up here is an actual just delta E. All right? On the right-hand side of the equation, we're also going to be essentially taking the integral of that dq and that dw. And when we integrate dq and dw, we end up with just q and w. So the total heat added or removed from the system, and the total work added or removed from the system. All right? And you'll notice that I kind of wrote, after the integrals, I kind of wrote the energy and the q's and w's in different formats. And to end this video, I just want to bring up a kind of subtle point about these different sort of properties. When we're dealing with energy, this sort of quantity is known as a state function. All right? And so when we're dealing with state functions, if we want to find the total change of a state function, all we need to consider are the endpoint values of that function. So only the endpoint values matter. Okay? And so when I integrated here, I just integrated from whatever the value was at time 1 to whatever the value was at time 2. All right? And so with a state function like energy, only the endpoint values matter. For heat and work, however, these are not state functions. these are what we call path functions. And so when we integrate them, this dq and dw, it actually matters, what the functional form of dq and dw are. And so to write that out, I'll write, so integrand function actually matters. And so the way to think of it is like this, is when we're dealing with q or w, what we're really saying is that q is going to be equal to the integral of q dot with respect to time from some initial time t1 to some later time t2. And for work, it's the same thing, where work is equal to the integral of the work rate with respect to time from t1 to t2. And so what I'm saying here is that when the integrand actually matters is whatever the function of q dot or w dot, whatever function represents them, that is actually going to affect what your total q and your total w values are.